So in this session, we look at how the Python implementation of policy iteration looks like. So what is policy iteration? We assume a random policy, and from that random policy we try to calculate the value function, and from that value function we see for we try to evaluate the Bellman equation, and depending upon the Bellman equation, if there is an improvement in the policy, we update the policy. Otherwise, we exit out of the loop. We continue until there is no changes with respect to the policy between the two consecutive time steps. That's the logic. So let's look at the code. So here you can see that here you can see that there is a random policy initialized. What is a policy? A policy is nothing but what action should we take at a given state. If state equal to 0, take value 2, take an order of 2. State equal to 1, then take value of 3. That is the vector that represents for a given state value what is the action that you should perform. That is nothing but called as the policy policy vector or the policy of the given problem. So we initialize a random policy here, and then what do? We enter into the loop. So for this given policy, first we need to compute the value function. How do we compute the value function? We can write these equations and then solve the set of linear equations, or what we can do is that we can do a iterative convergence, and in the iterative convergence approaches is what was taken here. So what do? We take a random value function. The value function is initialized to a random vector, and what do? Using this random vector, and by the using the given policy, we try to find the optimal. We try to find the updated value function. So here you can see for all states in the state space, we try to take the action suggested by the policy A equal to policy of S. So we take the action that was suggested by the policy, even though the action suggested by the policy is deterministic. The end state can be different because the demand is probabilistic in nature, and so for this specific action we try to calculate what is the value function, and depending upon this we since we have taken this specific action, we end up telling that the updated value function for the given state is equal to this value. And once this is done, we have a new value vector and a old value vector, and if the distance between the new and the old value vector is less than a threshold, it means that we have converged and we have obtained the value function that corresponds to the given policy. And if not, we continue this loop until this condition is satisfied. So this is how given a policy, we calculate the value function. So given the value function, now what we can do is that we can solve the Bellman equation, and if the action argmax of the Bellman equation has suggests a different action compared to what is suggested by the policy, we can update the policy. So how do we do that? So for the given action, we know what is the value. So that is nothing but v of s for a given state. For the given action that we have already taken using policy of x, we know what is the value function. What we can do is that we can loop over all possible actions for the given state and see if there is another action where the value function is more than this value, and if this action is different from what is suggested by the policy, we can update the policy, and that is what is performed here. And once the policy is updated, you will see that the optimal policy you will see that the optimal policy found boolean variable is set to false, and if this is set to false, that means the policy can be still the policy is not yet converged, and still it will, with this new policy we will get a new value function, and from the new value function we'll do a policy improvement, and so on. Between two consecutive loops in the policy improvement, if there is no change in in the policy, then this variable will be true, and this optimal policy found variable will be true. And if this optimal policy variable is true, then the final policy is predicted out. So here you can see that we are having two loops inside a bigger for loop. So it is computationally more expensive compared to a value iteration process, because for a given policy you need to do a convergence to get the optimal value function, and for that again you need to compute if there is a policy improvement or not. So let us look at how this code executes. So here you can see the initial policy is that was randomly selected was 20240, and the policy is updated around 6 times, and the final policy is 43210. As you can see here, if you remember in the value iteration also, this is the same policy that we have obtained after converging the value functions. So here if you can see, the final policy is also 43210. So uh, this is how the policy iteration is performed, and for a given stochastic inventory problem we can use both value iteration and policy iteration to converge to get the optimal policy and the optimal value function. But the downside of using policy iteration is that it takes more number of steps to converge compared to the value iteration process, because it needs to converge for the value vector first for a given policy, and then only can perform policy improvement. Thank you.